retired science teacher, taught science many, many years, many different subjects, including astronomy. And I love Mars, and I've always wanted to be an astronaut exploring Mars. And for the last 3 years, I've been able to explore Mars from orbit through the High-Wish program. It's a way of anybody suggesting pictures to be taken on Mars. It was called the People's Camera for many years. So every one of us can suggest pictures, and I've jumped into it because I love Mars. I feel like I've been in orbit around Mars for quite some time. And it's sort of like Spock, when Spock, when they get into orbit around a planet, and Captain Kirk says, Spock, analyze the planet, where it can land, and Spock looks at it and everything, and he says, well, do this and do that. Well, that's sort of what I did, but it took me a long time. Spock does it in a couple minutes. It took me 3 years to figure out where to land and so forth. So in this talk, I want to talk about the location and cause of Martian ice deposits. I think ice deposits are very important because if we want to colonize Mars, we need a supply of water. Just like when the Conestoga wagons came across, people had to find sources of water. And with water on Mars, you take the water apart and get oxygen and hydrogen for rocket fuel. So finding water is very important, and finding the closest water is important. And that's what most of my research was. And I want to talk about things I've found, and then I looked up the basic model for this, and hopefully I'll get done in time for the next one. There's many features on Mars that look like glaciers. So this is one that it looks like there was a glacier here, and what's happening here is probably there was a glacier full of ice, and this is sort of hollow here. So the ice is gone. It's melted, or it's actually sublimed. In the thin atmosphere of Mars, most of the water will directly change to a gas. And what's left is the moraines, the debris left by the glacier. And the next slide, this is a glacier that probably already has ice. So this is a good thing. If we find things like this, we can go there and perhaps harvest the ice. The center part is not hollowed out like the last feature. And it's kind of a convex shape on the top instead of concave. This is in the last one was the high-rise image. These high-rise images are about 6 kilometers across. They have a resolution that's 25 centimeters per pixel. So you need about 3 pixels to see something. So that means you can see something on Mars that's about 1 meter. And I found that they have found craters on Mars that are about 1 meter. They can't see them too much less than 1 meter, but about 1 meter. So that's like a table, like this table back here. So it's tremendous resolution. And we could all use this camera. Now, they found these things they call them lobate debris aprons. They seem to be around mesas. So here's a mesa, here's another mesa, and there's material around these mesas. They think these are glaciers. Like the glacier we saw before is like a preliminary thing, and then sometimes they coalesce or unite and get a wide glacier around these mesas. They call those lobate debris aprons. And we want to take it and enlarge this. This is a CTX image. The context image here has a resolution of 6 meters. So basically, with a picture like this, you can see things that are about the size of this room here, a little bit smaller in this room here. What I did was I studied these CTX images, and I found interesting things I thought, like here, and then I suggested that for a target. Then I had to patiently wait, maybe months and months, and then they finally took the picture. It takes a while for the process. And then we got this picture, got the next picture. So there's an enlargement of that. There's that mesa. And we're going to keep on enlarging that little area here. You get the image, and then there's a tremendous amount of data there. You have to slowly magnify it. And when you magnify it enough, you see these patterns, and we call this brain terrain on this side, because it looks like the surface of your brain. And there's two kinds. There's the wide kind, or the closed brain terrain, closed cell brain terrain. There's little bits of this narrow ridges, and that's the open cell brain terrain. Now, the people in the back probably can't see this. I usually show these with the lights way down low. We can't get them down anymore here. Now, another thing related to this is lineated valley fill. This has been seen for many years, and with high-rise we can enlarge this. So lineated valley fill, as the name says, is basically in valleys. Here's a high area. This is the mesa. Another mesa. It seems like what's happening is you've got the low-bait debris apron here, which is a glacier. Another low-bait debris apron here, a glacier. And they go together and they form these ridges. And these ridges often will be very long and sometimes straight, so we call it lineated valley fill. For this features, we're going to enlarge in this area here. And we're starting to see some patterns develop. And I like this picture, it's nice and clear. We can clearly see now the difference between the closed cell brain terrain and the open cell brain terrain. It's thought that the closed cell brain terrain, these ridges, they're kind of wide, and they contain a core of ice. And when that core of ice disappears, sublimates into the thin atmosphere, the middle section falls down, and you get two skinny ridges instead of one big ridge. And we call this open cell brain terrain. Most of the brain terrain on Mars is the closed cell. So this would be a neat place to look for maybe forms of life, or maybe even get the sources of water there. And then another related feature, these are all in the same area, and we can map these from orbit. So it's not like we land on Mars and then we walk around, we send out the robots to look around for these things. We can have all this mapped ahead of time. In fact, we have a lot of this mapped already. I've mapped a lot of it myself. Concentric craters, I have these concentric ridges, circle after circle ridges. And also, they are filled up, mostly. There's a whole bunch of stuff in it. It didn't form this way. It was a big open space in here. Now it's full of this stuff. And when we examine the surface, you see these ridges, and examine some more, we will see the brain terrain again. So all these features seem to have the same shapes. There's mostly the closed cell brain terrain, which has the water in it, ice probably. And then there's little traces here and there of the open cell brain terrain. And this little box, I put these boxes on for scale. That's like a football field. So I think it's kind of neat to walk around there, you know, with all these going up and going down. Now, our knowledge we know about impact cratering will give us clues to the nature of concentric crater fill. We know when a crater is formed, usually you have a bowl shape, deep bowl shape, and you have rims, and sometimes you have ejecta sitting out there. And this is true if you're on Mars or on the moon or different planets or on Earth. You can go into the next state, Arizona, and see a meteor crater. You'll see it has that bowl shape. Now, this is how the crater was first formed. And we know from experience that if you have a certain diameter, you should have a certain depth. And then we look at what we actually observe with the concentric crater field. It seems like it's filled up. So all this extra material is in there. And the current idea is that it is gotten in there, and it's mostly ice. In some cases, maybe almost pure ice. Research seems to be indicating that all these features have a thin layer of debris on top, and then the rest is ice or ice and dirt, and in many cases it's pure ice. So again, a nice place to go to get your water. So we've seen with these probable ice features, the low-bait debris aprons, the native valley field, concentric crater field, they have similar surface features. And now the first two, we pretty much have confirmed there's ice there. With our radar experiment on Mars Reconnaissance Orbital, we found there's a layer of debris, maybe a few meters thick, and then below that's pretty much pure ice for the first two features. And we're guessing that the concentric crater fields are the same sort of thing. So it seems like there's probably ice in these locations. Next, we're going to look at some ideas for how that ice got to these locations. We found this a long time ago. It seemed like many craters and much topography on Mars was smooth. And this smoothness is pretty much all over. It could be on top of the rims. It could be all over here. And many things were smoothed out. And it seems like there's rapid erosion or something. And now we seem to think that maybe something fell from the sky and covered everything with a smooth covering. And so we're going to talk about this thing. They call it mantle, or latitude-dependent mantle. I'm going to enlarge in this area here. And you can see that there's some places it's kind of rough. That's probably where there's no mantle. And there's some areas that's pretty much all smooth. That's probably where you have a fair amount of mantle. And what's interesting is that you seem to have layers in the mantle. Now I'll enlarge this so you can see the layers more. And this has about 4 different layers. Some researchers have found areas with 6 layers. And this seems to indicate that this mantle was fallen down repeatedly in the past, many times. Then we want to investigate the characteristics of this mantle. And one thing about the mantle is it has characteristics suggesting it has ice in it, or water ice. And here we have some gullies down here along this escarpment. We enlarged those with the high-rise image. What I did was I would look at an image just like this, a CTX image, and I would look at this and I said, well, it looks kind of interesting. There might be gullies there. Sometimes you can't really tell. You have to just guess. And then I submit a proposal, and I get a picture a few months later. And here you have these gullies. And gullies now are sort of accepted to be formed from running water. So in the last 1,000,000 years or so, these were formed. Now, 1,000,000 years isn't very much in geology. The southern part of Mars is billions and billions of years old. So 1,000,000 years is pretty young in Mars terms. And these particular gullies, they're basically formed right in the mantle. And if we think they're made for running water, where the running water came from the mantle. So the mantle probably contains running water. Many places on Mars, in certain locations, theory suggests that you have melting of ice, actually melted, for only maybe a couple hours in the afternoon, and for maybe a couple months. So every day around noon, a little bit of water melts, a little bit of ice melts, and then you get this water and you get erosion, and that's enough, they say, to make these gullies. So that's probably what's happened there. So there's evidence there that they contain water. And then here's another picture of the mantle. Now this is from the far north. This is Milankovic crater, and it's easily seen. It's in the far north in Mars, and it sits by itself. It's sort of north of Olympus Mons, the highest volcano, which a lot of us know. The mantle's very thick in this area. I'm going to enlarge this box over here. And what they have is these scallops. Now these scallops are kind of interesting. As you go farther north, the mantle breaks down into these scallops, and the scallops are associated with frozen ground on Earth. So when you see these scallops on Earth, it means it's frozen ground. And I'm going to enlarge this scallop there. You see something interesting. Hopefully we can see this. Some of us can see it. We have these polygons. The ground is shaped into polygons, and when we find polygons on Earth, we know there's frozen ground. And then here's a picture that shows scallops, and it shows polygons, and it shows these. There's some pits there. The scallops they form, they're small, and then they get bigger and bigger, then they coalesce and they get bigger, and then the northern part, or the part away from the equator, seems to open up. So they study these scallops a lot, and they're not exactly sure of all the details. Now we're going to enlarge this area here, the scallops, and here we see a picture that shows a lot of detail. I'm not sure if you can see, people in front probably can see there's these little boxes, polygons, and this is known as the low center polygon terrain. It is the middle section of these polygons is lower than the outside. There's like a ridge on the outside. And we have these in Rocky Mountain National Park, a couple hours drive from here, and again, it's characteristic of frozen ground. So if we're finding these polygons in many areas of Mars, so and they are in the mantle mostly, so we think the mantle contains a lot of frozen ground. So in summary, at this point, we see that the gullies are evidence of water ice in the mantle, and the polygons and scallops also evidence of ice, water in the mantle. And we saw the layers indicate that it might happen many times. And next we're going to talk about a model that kind of explains this. Now when they first analyzed these things, they basically looked at where everything was. They put dots on the map. And they spent a lot of time with all these things. The polygons and the gullies and the mantle and the concentric crater. They got the boxes. They put all these dots, and they found that almost all these features are found in certain areas. Between 30 and 60 degrees north and 30 to 60 degrees south. And so that suggests that climate is involved. It's like on Earth, certain areas you have tundra, certain areas you have desert, certain latitude regions. So same reasoning, the geologists, climatologists sort of thought there was something involved in climate. And then they've got other people involved, and it seems this is the current model for this. Currently, Mars has a tilt of 25 degrees compared to the Earth, 23.5 degrees. Now, the Earth's tilt stays almost the same all the time because we have a large moon relative to us. And as we know, Mars has two really puny, wimpy moons. And they can't really stabilize the tilt. So the tilt of Mars changes a lot. And when we look at the latest research, it seems like it's not very often at 25 degrees. It's often different than that. And many times it's a lot more than that. Sometimes 80 degrees or more. At this tilt, notice what we have is the sun's coming in from one side on this diagram, and with this kind of tilt, like the Earth, ice tends to accumulate at the poles because the light is not very intense there. The light is not very intense, so it's not too much heating. Now, when Mars changes its tilt, when it goes to 45 degrees, that seems to be the point where the light is intense enough to make enough heat to unstabilize the ice. So the water ice there sort of sublimates and turns into a gas. That gas goes around and then it will fall as snow other places. It also, on Mars, there's a lot of dust, so it often coats the dust grains. The dust grains get heavy and they fall down. So what we think is happening is the mantle is composed of snow and this ice-coated dust that falls down. And it will, according to our theories, it will go down to mid-latitudes. So those features we saw are found in mid-latitude. So we have the North Pole and the South Pole. In between would be where the equator would be. The equator is 0 degrees, and then the high latitudes would be at the poles. Mid-latitudes is sort of halfway there. And so we find a concentration of these features around 40 degrees or so north and south latitude. So you get a band of these features. Now, you have the 45-degree tilt, you might get a little more. Then it goes back. It goes back to the 23 or even back to 0. When it does that, some of the ice goes back to the poles. But what happens is you get a lot of dust there. So the ice sort of goes away, sublimates away. And you have a lot of dust there, so the dust falls down and caps it. And so it stays, every time you have this thing, it stays there. And now on the, a half a year later, the sun's on the other side of Mars, so the opposite thing will occur, and you'll get this mid-latitude snow and ice formed in the southern hemisphere. So in summary, find and understand the distribution of water ice is of utmost importance for the future colonization of Mars. And we've seen that the low debris aprons, lineated valley fill, and concentric crater fill are believed to contain ice, and they can be mapped from orbit, so we sort of can find out where the ice is. An ice-rich mantle seems to have fallen many times in the sky. This mantle sometimes contains layers, and evidence for it containing water would be gullies, polygons, and scallops. And the current idea is that changing the tilt of the planet's poles could have changed the climate of the deposit mantle. So that's how we stand now. You know, maybe a month from now it might change, but this is sort of what the models have evolved at this point. Thank you very much. We have time for questions? Okay, any questions? Yes, sir.
So this all seems like it's at 30 to 60 degree latitude. Could we expect an ice coating there, or is it only in certain locations?
Okay, I'm sorry, can we expect
an ice coating? So if we just pick a random location between 30 and 60 degrees, will there be ice there?
Not necessarily, but a higher probability there, much higher probability. If you see some of these features, which you can pretty easily see, then you have a real high probability. And we're talking about, some of them say 15 meters deep, but others say it's a couple of meters deep. So there's a lot of ice there, probably. Yes, sir.
So I don't know if there have been multiple theories about this, but what is the reason behind the northern hemisphere of Mars being at a generally lower elevation than the southern hemisphere?
Good question. And there's a lot of debate about that. And the latest seems to be that there was, early in Mars history, there was an oblique impact. So it was an impact crater. It didn't hit straight down. It came on an angle, a very sharp angle, or shallow angle, and it created like a depression there, sort of. And so, as a result, a lot of the material's it was blown up, and I guess it could have been blown out, or it might have just eventually fallen down to other parts of the planet. So there's a number of ideas on that, and that seems to be the most current one, and it might change in the future. There's a fellow down in Golden that does a lot of research on that. Yes, sir.
Is it possible that there could be large masses of frozen ice, such as basically underground glaciers that are flowing?
Yes.
That explains
Yes.
some of that? Because a lot of the stuff that you showed looked just like some sort of material flowing, or the results of it. But it seems kind of weird that we wouldn't see anything like that on the surface, but we believe it would be something subterranean.
Well, from the radar studies, it seems like there's, they say, a few meters of debris, dirt, dust, and then there's the glacier underneath. Just like a regular glacier, I mean, maybe, I don't know, hundreds of feet deep. I don't know if that answers your question, but it is flowing out. It's very cold there, so the ice is flowing slowly. But it's just like you said, there's glaciers there. We can map them from orbit. Yes, sir.
I know that Mars has pretty significant windstorms and seasonal changes out of weather patterns. Does that account for the movement and shifting of this mantle? And what's the difference between like the mantle and regrowth?
Okay, the mantle and the regular. Good question. The mantle will be like a covering that is finer than the regolith. Regolith would refer to everything there, would include the mantle, but also boulders and gravel and all those things. That would be the difference there. And the first part of your question was?
So I was just wondering how much of this could be attributed to wind erosion rather than necessarily
Wind erosion.
water flow.
I don't know, probably some, but remember the atmosphere of Mars is very, very thin. But obviously, wind erosion is involved there somehow.
Well, I was thinking if you dump the mantle or whatever into these craters, that, maybe that's why Max's kind of higher is the wind.
Oh, yeah, yes, that has been suggested, and what they're more now thinking of glaciers pushing things around, flowing and pushing things around. But the wind is a factor there. Wind is a factor in all this. And you may be able to see in the one I had these pits that were elongated. Now, we wonder what causes the pits to be elongated in the north-south direction and not in this direction. And the answer seems to be there's warm winds going in north and south, and that kind of melts more of the ice or takes it away. So that's one example where it's exactly like what you said. Yes, sir.
I'm surprised you speak of the mantle because I thought the mantle was covered by the crust, which is 7/10 of kilometers with.
Yes, the mantle is a bad term they use. There's the mantle that's above the crust, like you said, and this is another mantle involving the dust. Yes. How much time do we have? One more question. Yes, sir.
You mentioned public access to one of these cameras. Which camera was that?
Okay, the high definition pictures were all a high rise, and then some of the wide angles were CTX. That's all I showed today. Okay. Thank you very much.